Hello, chemistry students. In this video, you will learn definition of stoichiometry. You will learn definition of mole and Avogadro's number, definition of molar mass, and then we will see molar ratios from chemical formula and balanced equation. We will do some practice for conversion between grams, moles, and atoms or molecules. We will do problems related to reaction stoichiometry and theoretical yield. In reaction stoichiometry, we will see the problems related to dealing with limiting reactants. We will see the topic combustion analysis and find empirical formula and molecular formulas. The last topic will be going back and forth between formula and the percent composition. Let's see the definition of a stoichiometry. Stoichiometry is the quantitative relationship between components of a chemical reaction, and it can be thought of as chemical arithmetic. Look at this balanced equation. According to this balanced equation, we have 1 mole of hydrogen reacting with 1 mole of iodine and giving 2 moles of hydrogen iodide. So the quantitative relationship between the moles of reactant and product is we have 1 mole of hydrogen reacting and giving 2 moles of hydrogen iodide. Same is 1 mole of iodine reacting and giving 2 moles of hydrogen iodide. So this relationship that we are just using is the quantitative relationship. In this video, you will see if you have to make a certain amount of the product, then what amount of the reactant you should start with to get that certain amount of the product. Or if you have a certain amount of reactants given, how much of the product you can get from those reactants. So all that calculation is called chemical arithmetic or stoichiometry. We can understand stoichiometry with the help of this pancake recipe that I have here. And you will see that basically we use stoichiometry in our everyday life a lot. So per this recipe, we have to use 3 eggs to make a batch of 5 pancakes. Now, for instance, if I want to make a batch, I want to make 2 batches, means 10 pancakes. Now, what should I do? How much eggs should I use for that? Now, if your answer is that 6 eggs are needed to make 10 pancakes, it means you already know how to do the stoichiometry and adjust the reactants to make the product. Let's see mole and Avogadro's number. We will be using a lot the word mole, and basically starting from this chapter, all the translation of the equations we will be using with the word mole. Before this chapter, we were translating chemical equations with the help of molecule. Like we were saying, 1 molecule of hydrogen and 1 molecule of iodine reacts and give 2 molecules of hydrogen iodide. But starting this chapter, we are going to start using the word mole, and we will say 1 mole of hydrogen molecule reacts with 1 mole of iodine molecule and give 2 moles of hydrogen iodide molecule. Now, what is this mole? Mole, the symbol for mole is just MOL. So a mole is a unit of measurement for amount of substance. It is a SI unit, and we use it to represent the amount of substance. In quantitative terms, a mole is a substance, means you have 6.022 times 10 to the 23 of that thing. You can consider it like having a dozen eggs, means you have 12 eggs. So just treat this word mole as a dozen. It will be very easy to understand. For instance, 1 dozen of oranges means 12 oranges, 1 dozen banana means 12 bananas, 1 dozen egg means 12 eggs. So similarly, 1 mole of a substance or 1 mole of anything that you have equals 6.022 times 10 to the 23 of that substance. This 6.022 times 10 to the 23 is such a huge number that if you count every grain of sand on every beach and ocean floor on this planet, you would only come close to this number or close to 1 mole. So it is that big number. And this big number is called Avogadro's number in the honor of Italian chemist Avogadro's. He didn't actually discover this number, but his efforts towards the discovery of this number are great. So this number is named after his name. Let's do some practice of making conversion factor from mole and Avogadro's number. Remember that 1 mole of the substance equals 6.022 times 10 to the 23 of the substance. Now, let me write down some examples, and then you can pause the video and try making these conversion factor at your own, and then play the video to check your answer. So I have all these examples here. Now let's make a conversion factor between these moles and the Avogadro's number. So first of all, when we read these, it is 1 mole of hydrogen molecule. The second is 1 mole of hydrogen atom. The third is 1 mole of oxygen molecule. Fourth is 1 mole of oxygen atom. Fifth is 1 mole of water molecule. And sixth is 1 mole of glucose molecule. Now, when we make a conversion factor, it will be just the same, that we have 1 mole of hydrogen molecule equals 6.022 times 10 to the 23 hydrogen molecules. 1 mole of hydrogen atom equals 6.022 times 10 to the 23 hydrogen atoms. 1 mole of oxygen molecule equals 6.022 times 23 O2 molecules. Okay, 1 mole of oxygen atom equals 6.022 times 10 to the 23 oxygen atoms. And then we have 1 mole of water molecule equals 6.022 times 10 to the 23 water molecules. Here we have 1 mole of glucose molecule equals 6.022 times 10 to the 23 glucose molecule. Okay, our next topic is molar mass. Molar mass is the mass of 1 mole of an atom or molecule. To get 1 mole of any element, we take its atomic mass from the periodic table. All these decimal numbers in the periodic table are the atomic masses. So we simply take these masses, those are actually given in AMU, and we change the unit to gram. For instance, for hydrogen, 1.0079 AMU. When we change this AMU to molar mass, we simply change the unit from AMU to gram. And for moving forward, let's make this a standard that all the masses that we will take from periodic table, we will take them rounded up to 2 decimal place. For instance, if I have to use molar mass of hydrogen in a problem and I have to take the molar mass from the periodic table, I will round it to 2 decimal place. So it is going to be 1.01 gram instead of 1.0079. Okay, so just make this a standard for the rest of the semester. So let's do some practice of finding molar masses. So what is the molar mass of carbon? And if your answer is that molar mass is 12.01, then you are right. Molar mass of oxygen, when you round it to 2 decimal place, going to be 16.00 gram. Okay, so that's how we can find the molar masses for 1 mole of any element. But if you have a compound given, for instance, water, And if you have to find molar mass of water, it means you are going to add molar masses of all these elements that are in this compound. So for instance, for water, we have 2 hydrogen. Molar mass of 1 hydrogen is 1.01. You're going to multiply it by 2. You will have 2.02 gram. And then for oxygen, it is going to be 16.00 gram. You will be adding these masses, and molar mass of water is going to be 18.02 gram. Okay. Similarly, if you have to do, how about you guys do the molar mass of methane? Pause the video, do it at your own, and then play the video to check your answer. So molar mass of carbon from periodic table is 12.01. Molar mass of hydrogen is 1.01 gram. We have 4 hydrogens, so it is going to be 4.04 gram. When you add these, you will have 16.05 gram as a molar mass of methane. We normally write these molar masses in the form of a conversion factor when we use them in a problem. So molar mass is mass of 1 mole of a substance, right? So 1 mole of water is, so 1 mole of water is 18.02 grams of water. This conversion factor that I just made is called molar mass conversion factor, which is between mole and the mass of that substance. Similarly, for methane, you can make that 1 mole of methane is 16.05 grams methane. Let's do some more practice of finding molar mass. You can do this at your own and then play the video to check your answer. Molar mass of carbon from periodic table is 12.01. We are going to take up to 2 decimal place. For oxygen, it is 16, right? So 16.00 times 2. So it will be 32.00 gram. And when you add all these, it will be 44.01 gram is the mass of carbon dioxide. And if you're making a conversion factor, a molar mass conversion factor for carbon dioxide, it will be 1 mole of carbon dioxide is 44.01 grams of carbon dioxide. Another example, and again, do it at your own and then play the video back to check your answer. We have carbon 12.01 gram from periodic table. Hydrogen is 1.01. Let me underline all these that we are using. We have 1.01 gram, and then oxygen is 16.00 grams. So for carbon, we are going to multiply it by 6. Hydrogen will be multiplied by 12. Oxygen is going to be multiplied by 6. Okay, so carbon is going to be 72.06 gram. Hydrogen is going to be 12.12 gram, and oxygen will be 96.00 gram. You're going to add all these, and molar mass of glucose is 180.18 gram. So if you're writing in the conversion factor form, it will be 1 mole of C6H12O6, 180.18 grams of C6H12O6. In laboratory, we always work with masses because we cannot count moles or molecules. One of the way to convert moles to masses is with the help of a formula, and this is the formula that we have here. You guys can, it is good to know this formula and memorize this as well. So moles, which we represent with lowercase n. So mole equals mass in gram divided by molar mass. You will be using this formula for some of the problems, but for the 90% of the problems, we will be using unit analysis technique, where you will be using the molar mass conversion factor that you did the practice on the previous slide. Okay, let's do molar ratios from chemical formula. So molar ratios helps us identify how many moles of each element are present in a compound. So for instance, if I write a compound C6H12O6, if I read this formula, I will say it is 1 mole of glucose, right? So one that I'm taking is from here. There's no coefficient, means it is 1. So it is 1 mole of glucose, but the molar ratios of each element in this compound are that 1 mole of glucose actually have, so let me first write down, I am reading it as 1 mole of C6H12O6. Then this 1 mole of this have 6 moles of carbon. Okay, this have 12 mole of hydrogen. And by saying 6 moles of carbon means it is 6 moles of carbon atom. Okay, 12 moles of hydrogen atom. It have 6 mole of oxygen atom, right? Now, if you make a conversion factor of mole with Avogadro's number, so you know 1 mole of anything equals Avogadro's numbers, right? So 1 mole of glucose equals 6.022 times 10 to the 23 glucose molecules, right? That's a glucose molecule, so this is glucose molecule. So, but now for instance, this is given, 1 mole of glucose is given, and question is you have to find um, atoms of oxygen in it. So the mole ratio that we have is between the moles of a substance and the Avogadro's number, right? So if you have to find atoms of oxygen, means first you have to convert moles of glucose to the moles of oxygen, and then from moles of oxygen you can find number of oxygen atoms. Okay, this conversion that we are doing from here to here, we are doing this conversion is actually called mole to mole conversion. So mole to mole. Okay, there is, we have 1 mole of glucose. Here we have 6 mole of oxygen atom. So this is a mole to mole conversion that we did with the help of a formula. Once we have this mole to mole conversion, we can find the atoms of oxygen from here. 6 moles of oxygen atom you need to find. So you will be using Avogadro's number, which is 6.022 times 10 to the 23. Okay, so if you have to make a conversion between mole of oxygen atom, and here if you have 6 moles of oxygen atom, so 6 mole of oxygen atoms, and the mole ratio for, and the Avogadro's number mole ratio is 1 mole of oxygen atom is 6.022 times 10 to the 23 oxygen atoms, right? This is the normal conversion factor between Avogadro's number. So this will cancel, and when you multiply these two, you will get number of oxygen atoms. Now let's make molar ratios from balanced equation. Molar ratios helps us identify how many moles of product are formed from certain amount of reactant, as well as the number of moles of reactant needed to completely react with a certain amount of another reaction. So in order to do these molar ratios from a balanced equation, first of all, we have to make sure the equation given is balanced. So this equation, let's do the check. So we have 110 1 mole of tin, and here we have 1 mole of tin, so it is balanced. Here we have 1 mole of hydrogen, a hydrogen atom, and here we have 2 hydrogen atoms, right? Here we have 1 fluoride, and here we have 2. So it looks like in order to balance hydrogen and fluoride, we have to write 2 here, and this is going to make the equation balanced. So we have this balanced equation. Now the molar ratio is to identify how many moles of product are formed from the certain amount of the reactant. So for that, let's make a molar ratio between this product, which is tin to fluoride, and tin, and see what is the ratio we have. So if I make with tin, I have 1 mole of tin from the balanced equation. This one I took from here from the coefficient. So 1 mole of tin will produce 1 mole of tin to fluoride. Okay, and if I make this ratio with hydrogen fluoride, then it will be 2 moles of hydrogen fluoride react and produce 1 mole of tin to fluoride, right? And we can even make a molar ratio between these reactants as well. Like for instance, 1 mole of tin will completely react with 2 moles of hydrogen fluoride for a balanced equation, right? So that's a ratio for every 1 mole of tin, we need 2 moles of hydrogen fluoride. We can make these conversion factors between any two species. It can be between two reactants, between two products, or between a reactant and a product. We use these molar ratios when we have to do mole to mole conversions. And when we will be doing the stoichiometry problems, you will see that we will need these molar ratios a lot. Now let's see the conversion between grams, mole, and number of atoms and molecule. So there is a flow for these conversions, and flow is we convert grams. So gram is, for instance, you can say gram is your first point to start, and then you have moles in the middle, and then you have number of atoms or molecules at the third place. And the flow is grams to mole and moles to number of atoms or molecule. The conversion factor that will help you convert grams to mole is the molar mass conversion factor. A few slides back, we did the practice how to make a molar mass conversion factor. So that conversion factor will help you change the grams to moles. Now here I have divided the top and multiply at the bottom. You don't really need to memorize which operation to do in which direction. We will be using unit analysis technique, and in that technique it is very easy to determine whether you have to multiply with molar mass or divide. Okay, so you don't have to memorize that. So when you have to convert the moles to number of atoms or molecules, we use Avogadro's number. You have to memorize this number because it will not be given in exam. So 6.022 times 10 to the 23 is the Avogadro number that we use to convert moles to number of atoms or molecules. And again, you don't have to memorize whether you are going to multiply or divide because we will be using unit analysis technique. So the thing you have to remember is this flow, that always we have grams and then moles and then number of atoms or molecule. So for instance, if grams are given, if you have 40.0 grams of water given, and you have to find how many water molecules you have in it, there is no direct conversion from grams to molecules of water, right? You first have to convert these to moles of water, and from moles of water you will be converting them to number of water molecules. Okay, and again here you are going to use molar mass conversion factor, and here you are going to use Avogadro's number conversion factor. So let's do this example again. Pause the video, do it at your own, and then come back and check your answer. So how many grams of carbon dioxide are there in 1.20 times 10 to the 27 molecules of carbon dioxide? So here is the flow that we have. Molecules of carbon dioxide are given. So this is the part which is given 1.20 times 10 to the 27. So this is given and you have to find grams. Means first you have to change these to moles and then from mole you are going to convert it to grams. So that is my flow. So let's just start 1.20 times 10 to the 27 molecules of CO2. To convert the molecules to moles, we will be using Avogadro's conversion factor. And Avogadro's conversion factor is 1 mole of anything equals this Avogadro's number, right? So 1 mole, since this is molecule and we can only write molecule in the denominator to cancel, I will write mole at the top. So 1 mole of carbon dioxide is 6.022 times 10 to the 23 carbon dioxide molecules. This will cancel this part, and now we have moles of carbon dioxide. From moles of carbon dioxide to grams of carbon dioxide, we will use molar mass conversion factor. We find the molar mass of carbon dioxide in one of the slide before, but you can always solve it from the periodic table. So carbon is 12.01 gram, oxygen is 16.00 times 2 equals 32.00 gram. And when you add, you have 44.01 grams of CO2. Molar mass conversion factor that you will make will be 1 mole of CO2 is 44.01 grams of CO2. Now, since we want to get rid of the mole here, we are going to write down mole in the denominator. So 1 mole of carbon dioxide will come here and its mass in gram will be at the numerator, at the top. Okay. And then you are going to multiply everything that you have at the top and divide the numbers that you have at the bottom. And when you have multiple numbers at the top and bottom, suggestion is that to keep everything that is at the top in a bracket when you are adding these numbers on a calculator, and for divide as well, keep everything that is in the division in the parentheses. Okay, so on calculator I have 87698.439. Okay, we are going to round this to the proper number of sig figs. So here we have 3 sig fig, 4 sig figs, 4 sig figs. So if I round, I will be rounding it to these 3 sig figs. So I'm going to use scientific notation to convert this number to proper sig fig. 1, 2, 3, 4 places I am moving it to the left. This is going to be 8.77 times 10 to 1, 2, 3, 4 grams of CO2. So this will be your answer. Here we have another example. So do it at your own and then check your answer here. Okay, so for this problem, we have 500 grams given and you have to find moles. So we just have to do one step from grams to mole. So let's start this. 500.0 grams of methane is given and you have to convert it to moles of methane. We need molar mass conversion factor. Let's do it here. Carbon is 12.01 gram from periodic table. Hydrogen is 1.01 times 4.04 gram. When you add all these, we have 16.05 grams of methane. When we write in a conversion factor form, it is 1 mole of methane is 16.05 grams of methane. Okay, we need to get rid of the gram here, so we are going to write down 16.05 gram methane in the denominator, and the top is going to be 1 mole of methane, and that's it. That's all you have to do, one step. So your answer is 31.1526, but we need 4 sig figs here, 4 sig figs here. So 4 is the least number. We are going to round it to 4 sig fig. And when we do that, so we have 31.15 moles of methane. This is going to be your answer. Okay, here we have another example. So let's do it. 3.50 moles of ammonia is given. You have to find number of grams of ammonia. So moles of ammonia given, you have to go this direction to find number of grams of ammonia. Okay, so you need molar mass conversion factor here. So let's first start this problem and then we will make molar mass conversion factor for ammonia. 3.50 mole ammonia. Nitrogen is 14.01 gram. Hydrogen is 1.01 grams times 3, 3.03 gram. When you add, you have 17.04 grams of ammonia. When we make a conversion factor, it is 1 mole of ammonia, 17.04 grams of ammonia. Okay, so you can, we want to get rid of the mole, right? Moles of ammonia. So we will be writing 1 mole of ammonia in the denominator, and the numerator will be 17.04 grams of ammonia. So you cancel these, and when you multiply these two numbers, you will have your answer. Okay, here we have 3 sig figs, 4 sig figs. You need to round this to 3 sig figs. So when you do, you will have 59.6 grams of ammonia. This is going to be your answer. Okay. For B, you have to find number of molecules of ammonia. So whenever it is a number of molecules or number of atoms, means it is related to Avogadro's number. It is here, right? So you have to find number of molecules of ammonia. To get the number of molecules of ammonia, you have to start with moles of ammonia. So moles of ammonia is given. So we are going to again start with this number. And this time we are going to change this number from moles to molecule. And we need Avogadro's molar mass. So we will make that conversion factor in a minute. So let's start writing. We have 3.50 mole of ammonia. We need Avogadro's number conversion factor for ammonia. So that Avogadro's number conversion factor is, 1 mole of anything. So this time we have that as ammonia. So 1 mole of ammonia, and this is ammonia molecule, right? So 1 mole of ammonia molecule is 6.022 times 10 to the 23 ammonia molecule. We want to get rid of the moles of ammonia, so this mole will be in the denominator. So we have 1 mole ammonia here, and 6.022 times 10 to the 23 ammonia molecule at the top. So this will cancel. When you multiply these two numbers at the top, you will have your answer. So my answer is 2.1077 times 10 to the 24. And again, I will check my sig figs. So I have 3 sig figs here, 4 sig figs here. So I'm going to round it to 3 sig figs. And when I do that, it will be 2.11 ammonia molecules. That's what I have to find, molecules of ammonia. So for number C, one thing that I want to caution you about stoichiometry chapter is that you have to be really careful about the wordings. Like for instance here, if you read B, it is number of molecules of ammonia. If you are finding molecules of ammonia, right, you will start with moles of ammonia. But in C, you have to find number of atoms of hydrogen. So this time you have to find the same thing like atoms, but these are the atoms of hydrogen. Okay. Now, if you have to find atoms of hydrogen, you need moles, right? But you need moles of hydrogen. And the given here right now is moles of ammonia. So it means first you have to convert these moles of ammonia to moles of hydrogen atom, and then you will convert those moles of hydrogen atom to number of hydrogen atoms. So for C, remember, so the first step now we have 3.50 moles of ammonia given, and you have to find how many moles of hydrogen we have in it. Remember, we did the molar ratio from the formula in one of the slide here. So we have 1 mole of glucose here, and we converted these moles of glucose to the moles of each element. Like 1 mole of glucose have 6 moles of carbon atom, 12 moles of hydrogen atom. The same thing we have to do with the ammonia. So we have to make a conversion factor between moles of ammonia and the moles of hydrogen. I'm making conversion factor here. So we have 1 mole of ammonia. And in this 1 mole of ammonia, we have 3 moles of hydrogen atom. So this is my conversion factor that will help me change the moles of ammonia to the moles of hydrogen atom. So if I use this here, I want to cancel the moles of ammonia, so that is going to be the denominator, and 3 moles of hydrogen atom is going to be the numerator. Or this is cancelled, and now I have moles of hydrogen atom. So remember here, to get the number of hydrogen atom, we need moles of hydrogen atom, right? So we have now we can simply use the Avogadro's number conversion factor. So we have enough practice of writing those conversion factors right straight in the unit analysis problem. I want to get rid of the moles of hydrogen atom, so I'm going to write 1 mole of hydrogen atom in the denominator, and 1 mole of anything equals 6.022 times 10 to the 23 hydrogen atoms. All right, so this is cancel, this is cancel. Now you have to multiply all these numbers that you have at the top, and for denominator we have just 1, so we don't have to divide by anything. So your answer is 6.323, 1 times 10 to the 24. We will do our sig fig check. We have 3 sig figs here. This 3 is the exact number. This is your 4 sig figs. So I need only 3 sig fig in my answer. It is going to be 6.32 times 10 to the 24 hydrogen atoms. And that is my answer. Here we have another example, so do it at your own and then you can check your answer. Okay, so we have 0.565 moles of hydrogen iodide given. You have to find how many grams of hydrogen iodide. You have to go this way. You need molar mass of hydrogen iodide. Now we are going to make these conversion factors right in this unit analysis. 1 mole of hydrogen iodide is what I need to cancel. So 1 mole of hydrogen iodide. Here I need the molar mass of hydrogen iodide, which is 127.02 grams of hydrogen iodide. So this is cancelled and you have grams of hydrogen iodide in your answer. So you're going to multiply these two numbers that you have at the top. So your answer is 71.7663 grams of hydrogen iodide. We have 3 sig figs here, 5 sig figs here. We're going to round it to 3 sig fig. It will be 71.8 grams hydrogen iodide. Next, you have to find how many hydrogen iodide molecules you have. So here you have molecules. To find molecules, you have to start with the moles of hydrogen iodide, and you are going to convert moles to molecules with the help of Avogadro's conversion factor. So we have 1 mole of hydrogen iodide. So 1 mole of anything, right? So 1 mole of hydrogen iodide is 6.022 times 10 to the 23 hydrogen iodide molecules. So this is cancel and your answer is 3.40243 times 10 to the 23. We have 3 sig figs here, 5 sig figs here. So 3 sig fig is going to be in your answer. So it will be 3.40 times 10 to the 23 hydrogen iodide molecules. Now that we have a good practice of converting grams to moles and moles to number of atoms and molecules, we also have the practice of making a molar mass conversion factor and Avogadro's number conversion factor. We will use all that knowledge in the reaction stoichiometry. So this problem that we have now is from the reaction stoichiometry. We have tin reacts with hydrofluoric acid to produce tin 2 fluoride and hydrogen gas. Equation is given and we have to find how many moles of tin 2 fluoride will be produced from the reaction of 100 grams of hydrogen fluoride. Assume there is enough tin to completely react with hydrogen fluoride. So in this problem, there's some information given that hydrogen fluoride is 100 gram, and for tin, we just don't have to worry about how much we have. We just know that it is enough to completely react with hydrogen fluoride. And once this 100 gram of hydrogen fluoride is completely converted into the product, the reaction will stop. We have to find moles of tin 2 fluoride, and in the second part we have to find actually grams of tin 2 fluoride. So one thing for all the reaction stoichiometry problem is that you have to start with a balanced equation. In this problem, the equation is balanced, it is given, but it is always good to still check whether it is correctly balanced or not, because if the equation is not correctly balanced, then you will end up with the wrong answer. So we have 110, 110 here. We have two hydrogen. We have 2 fluoride and 2 fluoride. So this is balanced equation. Now the given is we have 100 grams of hydrogen fluoride. For all the reaction stoichiometry problems, we will be doing some strategy to solve the problem. So the workflow is that you will convert the grams of the species, like it can be reactant, it can be product, anything that is given, right? So you will be converting the grams of that substance to the mole. From mole, you will convert the mole of this substance to the mole of the substance that you are going to find. In this case, you are going to find tin 2 fluoride, so you are going to convert the mole of hydrogen fluoride to the moles of tin 2 fluoride. For this first part, you're going to stop here because you need to only find moles. But for the second, you also need the grams as well. So you can convert these moles to the grams of the substance as well. Now, the conversion factors that will help you do is from grams to mole. We did a lot of practice for this. The grams to mole conversion will be with the help of molar mass conversion factor. And you know how to make that. And here as well, mole to gram conversion will be with the help of molar mass conversion factor. Now, this mole to mole conversion that we have here in the middle, this mole to mole conversion will come from the balanced equation. There's 2 moles of hydrogen fluoride and 1 mole of tin 2 fluoride. This will help you convert the moles of hydrogen fluoride to moles of tin 2 fluoride. Okay, so this will be from equation. And this flow chart that I made, it can be between any 2 species. Right now, we made it between a reactant and a product. It can be actually made between a reactant and other reactant. For instance, if 100 gram of hydrogen fluoride is given and you have to find how many grams of tin you need to completely react with 100 gram, you will be converting the grams of hydrogen fluoride to moles, and then you will go here in this direction, change the moles of hydrogen fluoride to moles of tin, and then from moles of tin to moles of grams of tin, right? So this workflow that you have, you can make it any between any 2 species. So let's solve this problem. We will be simply following this workflow that we have created here. So our first step is we have 100 grams given for hydrogen fluoride, and we have to convert it to moles of hydrogen fluoride. Conversion factor, molar mass conversion factor is 1 mole of hydrogen fluoride equals, you need to find molar mass of hydrogen fluoride. Let's do this scratch work on the side. Fluoride is 19.00 gram. Hydrogen is 1.01 gram. So their molar mass is going to be 20.01 gram. So 1 mole of hydrogen fluoride is 20.01 gram hydrogen fluoride. Now we have moles of hydrogen fluoride. To convert moles of hydrogen fluoride to moles of tin 2 fluoride, we will get help from the equation. We will find mole ratios. So we have 2 mole of hydrogen fluoride and 1 mole of tin 2 fluoride. Okay, so now this mole of hydrogen fluoride is cancelled, and you have moles of tin 2 fluoride in your answer. Now for this problem that we are doing, broke in 2 steps. So the first step is just to find moles, so I will stop here. And I have 2.4987 moles of tin to fluoride. If you have to round it to proper number of sig fig, it is going to be 4 sig figs, right? So this is going to be your 4 sig figs under this. But since we are going to use this number in the next step as well, so I will just use the whole number for the next step. For the next step, I will use the unrounded number so that I don't do too much rounding at the end. We need again molar mass conversion factor. This time we need molar mass of tin 2 fluoride. So tin is 118.71 and fluoride we have 19.00 times 2. You're going to add these numbers, and when you add, your answer is 156.71 gram. So you multiply this by number of moles of tin 2 fluoride, and your answer is 391.57127. And again, when you round it to proper number of sig figs, so remember here your sig figs will be under this bracket. So we have 4 sig figs here and 5 sig figs here. This bracket came from here, okay? So just in case. So this came from here. So 4 sig fig there and 5 sig fig here. 4 is the least number. You are going to round it to 4 sig fig. It will be 391.6 grams tin to fluoride. This calculation that we did in this problem is the 100% conversion or complete conversion of the reactant into the product. Like this 100 gram of hydrogen fluoride, when completely convert into product, we will get 391.6 gram. And this complete conversion is called theoretical yield of the reaction. So the theoretical yield is the maximum amount of the product that can be made from a chemical reaction if all the reactant is converted into the product. But in actual, when we perform these experiments in lab, there are many reactions have competing side reactions that consume some of the reactants to produce unwanted product, and we call them side products. And sometimes we have difficulties in collecting and purifying the product, and some of the product may lost. You have done many experiments in this course. Like one of the experiment that we did is separation of salt and sand, and you know that it was very difficult to separate a pure product. It was a mixture was given, and the goal was to separate the components of the mixture. So you lost some of the product during the purification process. And generally, the actual yield comes out less than the theoretical yield. And that ratio between the actual yield that you get from the experiment and the theoretical yield, that is the 100% conversion. So this ratio multiplied by 100 is called the percent yield. And this percent yield actually gives how successful the reaction is. Normally, we get the percent yield of 70 to 80%, and those reactions are considered good or successful reactions. And if a reaction have the percent yield or actual recovery of like less than 50 or 30-40%, those are not very successful or good reactions. So here we have example, if the actual yield of the tin to fluoride reaction that we did in one of the previous slide, if the actual yield is 311 gram, what is the percent yield? So let's go back and see what was the theoretical yield. So theoretical yield for this reaction is 391.6 gram. So let's write down here. So theoretical yield is 391.6 gram, and the actual yield that we have from the reaction, okay, is 311 gram. You have to find what is the percent yield of the reaction, and here is the formula for that. So the percent yield for this reaction is 79.4177 percent, and you're going to round it to 3 sig fig because here is your 3 sig fig in this, right? So it will be 79.4%. Let's see what is dealing with a limiting reactant. The reagent that limits how much product will produce is known as the limiting reagent or limiting reactant. It happened that sometimes the reactants are not in exactly the right amount or in a balanced fashion, and one of them will run out before the other one. The one that will run out is called the limiting reactant. So, for instance, if I write the reaction between hydrogen and nitrogen to produce ammonia, and the balanced equation is that we need 3 moles of hydrogen for every 1 mole of nitrogen. So this is our balanced equation. The mole ratio between nitrogen and hydrogen is 1 to 3 for a balanced reaction. But in actual, if we have 3 moles of hydrogen given and we have 2 moles of nitrogen given, and we have to find how many moles of ammonia will produce. So even though we have 2 moles of nitrogen, it is more than what we need, but and the reactants this time given are not in a balanced fashion. The balanced reactants are we need 3 moles of hydrogen and 1 mole of nitrogen. But actual reactants given are 3 moles of hydrogen and 2 moles of nitrogen. The reaction will actually depend on the moles of hydrogen, and when the hydrogen is completely converted into ammonia, the reaction will stop and there will be some of the nitrogen left over. The reactant that will actually run out first is called the limiting reactant. So in this example that I just mentioned, so hydrogen is going to be our limiting reactant. Now, the problem that we did in one of the previous slide, if you look at this wording that we have, grams of hydrogen fluoride was given, and for tin, the instructions were that assume there's enough tin to completely react with hydrogen fluoride. It means in that problem they were already identifying it for us that hydrogen fluoride is the limiting reactant. So we have to start working with hydrogen fluoride and convert the hydrogen fluoride to the product. But it will not happen all the time. And sometime you will see that the reactants, that both reactants are given, and first step for you will be to identify the limiting reactant. So we will see how to do that. So in this example, let's first write down the balance equation. So the reaction is how many grams of ammonia can be produced from 25 grams of hydrogen and 50 grams of nitrogen. So we have hydrogen. So let's balance this equation. So we have 2 ammonia here and 3 hydrogen. So now it is balanced. We have 25.0 gram of hydrogen and 50.0 gram of nitrogen. And unlike the previous example that we did, they already identified it for us that hydrogen fluoride is the limiting reactant. But here we have to find which one is the limiting reactant. So the steps to find the limiting reactant is first you have to convert the grams to moles. Okay. Then you will divide those moles by their coefficients. Okay, coefficient is this number here. So coefficient for hydrogen is 3, and when you convert the grams of nitrogen to moles, you are going to divide it by its coefficient, which is 1 in this case for nitrogen, right? And this grams to mole conversion will be with the help of molar mass, right? This ratio that we will have is called mole to coefficient ratio, and smallest mole to coefficient ratio is the limiting reactant. So let's find it for hydrogen first. We have 25.0 grams of hydrogen given. We have to convert it to moles. 1 mole of hydrogen molecule is 2.02 grams of hydrogen molecule. So you have 12.376 to 3 moles. You have to divide it by coefficient, which is 3. You have a number. Mole to coefficient ratio is 4.125. That's the ratio. I'm not going to write down anything here. So this is if you have to just find number of moles of hydrogen from here, you are going to round it to 3 sig fig, and it will be 12.4 moles of hydrogen. And this is the ratio that we have. Okay, let's do it for nitrogen now so that we can compare and find which one is the limiting reactant. 50.0 gram nitrogen. We are going to convert it to moles of nitrogen. 28.02 grams of nitrogen. This is cancelled. 1.78444 moles. divided by 1 because coefficient for nitrogen is 1, right? It is going to be again the same number. Okay, we are only comparing these numbers, so you don't have to worry about the sig figs and all those things here. But if you have to round this to the number of moles of nitrogen, then it is going to be 3 sig figs. So it is 1.78 moles of nitrogen. Now you're going to compare these numbers to identify which one is the limiting reactant, and smallest ratio will be the limiting reactant. So your nitrogen is limiting reactant. So that is the first step. Once you identify the limiting reactant, the rest of the steps are exactly same as we did in the tin 2 fluoride example. So let's do the rest of the steps now. So we have identified that nitrogen is our limiting reactant. So we have grams of nitrogen. I'm making the flow chart again, right? For all reaction stoichiometry problems, it will be good if you start with the flow chart, have your strategy ready, and then you solve the problem. So 50 grams, you're going to convert them to moles, and then from mole, you are going to convert it to moles of the reagent that you have to find, which is ammonia in this case, and then you are going to convert it to the gram. So from here, mole to grams to mole conversion, you need molar mass. This as well, you need molar mass, and this will come from equation. This one, we did it in the previous step, so it is up to you. You can take the number from there, which was 1.78 moles of nitrogen. So you can start from there, or you can start from 50 grams of nitrogen, and then you have 1 mole of nitrogen and 28.02 grams of nitrogen. This is cancel. Next step is mole to mole conversion between moles of nitrogen to moles of ammonia. We have 1 mole of nitrogen, 2 moles of ammonia, and then from moles of ammonia to grams of ammonia, we find the molar mass of ammonia in one of the previous slides. You can take it from there. So 1 mole of ammonia is 17.04 grams of ammonia. All these are cancelled, and we have grams of ammonia in our answer. So you are going to multiply everything that is at the top and then divide by the denominator. And remember, when you have many numbers to multiply and divide, use parentheses to separate the multiplications and divisions. So I have 60.8137. If I round it to 3 sig fig, which is the lowest number that I have, my answer is going to be 60.8 grams of ammonia. Let's do another example. In this slide, actually, I have broken down the reaction stoichiometry problem in 5 steps. So if you look at these 5 steps and you do the practice for all these, you can do all reaction stoichiometry problems. The first step is write the balanced chemical equation. So the reaction is between chlorine and fluorine. So we have to balance this equation. To balance it, we're going to write 2 here so that we can get 2 chlorides. This will change the number of fluorides to 6. To get 6 fluorides, we are going to write 3 here. So now this equation is balanced. We have 10.0 grams of chlorine and 10.0 grams of fluorine. So when the masses of both reactants are given, we have to find the limiting reactant, right? So the steps for the limiting reactant are, remember, we are going to convert these gram to mole and then divide by their coefficient. And smallest mole to coefficient ratio will be of the limiting reactant. And we are going to do this for both of these reactants. Let's first do it for chloride. So we have 10.00 grams of chlorine. To convert grams to moles, we need molar mass. And molar mass of chlorine you can get from a periodic table. So 1 mole of chlorine, one atom of chlorine is 35.45 gram, and we have 2 Cl, so we are going to multiply it by 2. We'll get 70.90 grams of Cl2. So this will give you moles, 0.14267 moles of Cl2. You're going to divide it by the coefficient, which is 1 for chlorine. Here it's 1, right? So you will get 0.14267. If you have to round it to the proper number of sig figs, it is going to be 4 sig fig, 4 sig fig. So this is going to be your 4 sig fig, and if you do the rounding, it will be 0.1427 moles of Cl2. Next, let's do this for fluorine. We have 10.00 grams of fluorine. Molar mass of fluorine is 1F is 19 grams, so 2Fs will be 19 times 2, 38. And I'm taking this molar mass from periodic table. 10 divided by 38 is 0.263157 moles of F2. You're going to divide it by coefficient, which is 3, and you will get 0.0877. If you have to round it to proper number of sig fig, we have 4 sig figs here and 4 sig figs here. So your 4 sig fig is going to be up to this point, right? And it will be 0.2632 moles F2. Okay. Now to find which reactant is the limiting reactant, you will be looking at these two numbers. So you compare, and the smallest mole to coefficient ratio will be of the limiting reactant. So F2 fluorine is the limiting reactant. If fluorine is your limiting reactant, it means the product of the reaction depend on the grams of fluorine. 157 moles of F2. We need to do mole to mole conversion, which is from equation. So we have 3 moles of fluorine and 2 moles of chlorine trifluoride. So I'm going to write 3 moles of fluorine and 2 moles of chlorine trifluoride. So this will cancel here. Now we have moles of chlorine trifluoride. Next step is to convert moles of chlorine trifluoride to grams of chlorine trifluoride with the help of molar mass conversion factor. So 1 mole of chlorine trifluoride is 92.45 grams, and you know how to find the molar mass. We did a lot of practice, but let's do one more time here how I did it. So chlorine is 35.45 from periodic table. F is 19.00 from periodic table. We have 3 fluorides, so I'm going to multiply it by 3, and then we will add all those numbers. So 19 times 3 is actually 57. So this is the molar mass of chlorine trifluoride. Moles are cancelled, and you have 16.2192 grams of ClF3. Okay. Now the sig figs, this number have actually 4 sig figs up to this point, right? So under this bracket, we got it from here. So 4 sig figs here, these are exact numbers, and 4 sig figs here. So if we round, we're going to round it to 4 sig figs. So it will be 16.22 grams of ClF3 will be the answer. So we did, so this one is the theoretical yield of the reaction when we convert 10 grams of fluorine completely into the product. Now, the next is how many grams of excess reactants are left over at the end of the reaction. So remember, the chemical reactions follow law of conservation of matter, which is matter not created nor destroyed. So you are starting with actually 20 grams of the reactants, right? 10 grams fluorine, 10 grams chlorine. So 20 grams of reactant you are starting, and your product is 16.22 gram. So there will be some of the leftover chlorine because that's in excess. To get how much of the chlorine is left over, you can simply add all the reactants that we have and then subtract the product, which is 16.22 grams, right? So you do this and then you will able to find the leftover. So leftover for this is 3.78 grams, and that leftover is actually the chlorine, right? Because fluorine is the limiting reactant, will convert 100%. So this much grams of chlorine will be excess. And the last step is when the reaction is exactly performed, 12.5 grams of ClF3 is recovered. What is the percent yield of the reaction? This one is actually the actual yield of the reaction. And if you remember the formula, so the formula is actual yield divided by theoretical yield, which we have 16.22 grams, multiply 100%. So the percent yield for this reaction with 4 sig figs is 77.07%. Our next topic is combustion analysis. Combustion means burning, and burning something means reacting it with oxygen. When a compound is burned, all the elements in that compound actually combine with oxygen. So here in this example, I have a hydrocarbon. Hydrocarbons are the compounds that are mainly consist of carbon and hydrogen, and there might be a few hetero elements or some other elements beside carbon and hydrogen. So this is a hydrocarbon. When this hydrocarbon reacts with oxygen, all the carbon that we have will convert into carbon dioxide, and all the hydrogen will convert into water. This combustion analysis technique is very useful to determine the formula of compound that mostly contain carbon and hydrogen. And how we do that is when we burn a hydrocarbon in the presence of oxygen and we get carbon dioxide, which is all carbon came from this compound, and the water where all hydrogens came from here. If we trap these two products and we find the grams of the carbon dioxide and grams of water, we can convert the grams of carbon dioxide to moles of carbon dioxide, and from moles of carbon dioxide, we can find moles of carbon. And all these moles of carbon are actually came from this compound, right? So if we want to know what is the formula of the compound, we normally do it to find the formula of a unknown compound which is newly discovered, right? So when we do this and we find the grams of carbon dioxide and convert those grams to moles, and from moles to moles of carbon, that can actually tell how many moles of carbon we have in that unknown compound. Similarly, we can convert the grams of water to moles of water and from moles of water to moles of hydrogen, and that will tell us how many moles of hydrogen we have in that unknown compound. For oxygen, we have a little bit different calculation that you will see when we will do the actual formula determination from the combustion analysis. So I will hold on to that step until we see that problem. Let's see the difference between empirical formula and molecular formula. Empirical formula is the simplest formula that shows the ratio of the moles of each element in a compound. And molecular formula is the actual composition of the compound. For instance, I have this glucose molecule C6H12O6. This formula tells me the actual composition, means it tells me that it has 6 carbon, 12 hydrogen, and 6 oxygen atom. But if I simplify this formula and I get only the ratio between these, then the ratio is I have 1, 2, and 1. Means my hydrogen is twice compared to the number of carbon and oxygen we have. So this simplest formula that is giving me only the ratios is our empirical formula. Okay, and with the help of combustion analysis, we get the empirical formula. Now let's do this problem to find the empirical formula of a compound. So in this example, a compound containing carbon, hydrogen, and oxygen is subjected to combustion analysis. 30.03 grams of compound produced 43.5 grams of carbon dioxide and 23.5 grams of water. What is the empirical formula? Now, you don't really need the equation for these problems, but I always find helpful to have some equation there. We don't know what is the formula, but I will still write that we have a compound that consists of carbon, hydrogen, and oxygen. We don't know how many moles of carbon it have, how many moles of hydrogen it have, and how many moles of oxygen it have, but it is a combustion analysis, so it's going to burn with oxygen, and after that reaction it will give us carbon dioxide and water. Now we have 30.03 grams of this compound, right, that consists of carbon, hydrogen, and oxygen, and we have 43.5 grams of carbon dioxide and 23.5 grams of water. Now, the steps to find empirical formula are given here. Like first step is you have to convert the grams of carbon dioxide to moles of carbon dioxide, then convert the grams of water to moles of hydrogen. Then you have to calculate the grams of carbon and hydrogen from the moles of carbon and hydrogen. You will subtract the sum of carbon and hydrogen grams from the grams of sample, and this will give you the grams of oxygen. Then you will convert the grams of oxygen into the moles of oxygen, and then at the end you will divide all the mole values by smallest number to obtain the subscript in the empirical formula. So steps are here, but it is always good to do the some strategy for all the stoichiometry type of problems for the empirical formula as well. So what I'm going to do here is I will convert these grams to moles of carbon dioxide. Okay, from here I'm going to convert it to moles of carbon, right? The mole ratio here in carbon dioxide and moles of carbon is 1 to 1 ratio, right? From this formula, so whatever moles I will have here will be my moles of carbon, and once I have my moles of carbon, this is actually my x, right? So I will know that moles of carbon are this much, right? Here I will convert this gram to moles of water, and then from moles of water, I will convert it to mole of hydrogen. And here you can see moles of water and moles of hydrogen. The mole ratio is 1 to 2. 1 mole of water have 2 moles of hydrogen. And once I have these moles of hydrogen, that is actually my Y, right? So I have X and Y once I'm done up to this point. The next step is I have to find this Z, right? For Z, if you look at here, this 30.03 gram is actually the masses of carbon plus mass of hydrogen plus mass of oxygen atom, right? So this is the sum of all these masses. If you subtract, now we have the moles of carbon and hydrogen, right? So if you convert these moles of carbon and hydrogen to the grams, right? You convert it to grams of carbon and grams of hydrogen. Once you have these, you add these grams, right? And then you subtract these grams from this total mass of the sample, which is the gram of carbon plus hydrogen plus oxygen. When you do this, what will you get? You will get grams of oxygen, right? Once you have grams of oxygen, you can actually convert these grams of oxygen to moles of oxygen, right? With the help of molar mass conversion factor. So this mole of oxygen is actually your Z, right? That's what you have. Now, the reason why we cannot find moles of oxygen from the carbon dioxide and from the water the similar way we find the carbon and hydrogen is because part of the oxygen came from this hydrocarbon and most of it came from the environment. So we actually don't know how much is from this compound, right? So to find how much is exactly from this compound, you have to follow these steps. Okay. And once we have all these XYZs, we are ready to do our step number 6. So let's go ahead and start this problem now. So number 1 is we are going to convert grams of carbon dioxide to moles of carbon dioxide. So moles of carbon dioxide, we did that practice. It is 44.01 grams of carbon dioxide. So we have moles of carbon dioxide. We can convert this to moles of carbon. The mole ratio is 1 to 1. It is going to be 0.98841 moles of carbon. And if you have to round it to proper number of sig fig, which is 3, then it is going to be 0.988 moles of carbon. Okay. Next step is we are going to convert grams of water, which is 23.5 grams of water, to the moles of hydrogen. So first step, we are going to convert 1 mole of water is 18.02 grams of water. This is cancel here. 1 mole of water. So mole ratio between mole of water and moles of hydrogen is 1 to 2. So it will give you 2 moles of hydrogen. So we have 2.608 moles of hydrogen. And if you have to round it to proper sig fig, we have 3 sig figs here. So it is going to be 2.61 moles of hydrogen. Okay. Next step, remember we have to calculate the grams of carbon and grams of hydrogen. So let's do this here. We have 0.988 moles of carbon. 1 mole of carbon is 12.01 gram of carbon. It is 11.86588 grams of carbon, and rounded to the proper number of sig fig, which is 3, it will be 11.9 grams of carbon. Next, we are going to convert moles of hydrogen to grams of hydrogen. rounded to proper number of sig fig is going to be 2.64 grams of hydrogen. Next, you are going to add these two. Um, this will give you, and then you will subtract it from 30.03 grams. Okay, so 30.03 minus 11.9 minus 2.64. You have 15.49 grams of oxygen. To convert the grams of oxygen to moles of oxygen, you're going to divide it by its molar mass, which is 16 grams, and it will give you moles of oxygen, which is 0.96825 moles of oxygen. If you round it to proper sig fig, will be 0.9681 mole of oxygen. Okay, so we have moles of oxygen, carbon, and um, hydrogen now. Now we're going to do number 6, which is divide all mole values by smallest number to obtain the subscript in the empirical formula. So we have our carbon. Number of moles of carbon that we have is 0.988. Hydrogen we have 2.61. Oxygen we have 0.9681. So the smallest number of mole is oxygen, 0.96. So we will divide all these by this number. Okay, so let's see what we have when we divide these. So here for sure it will be 1 because that's the same number. For hydrogen, I have 2.686. For carbon, I have 1.02. So here we cannot use our normal rounding rule. We have to find a multiplier that can convert all these coefficients to a whole number. So if we multiply all these by 2, then let's see what we get. So if you multiply carbon by 2, then it will be 2.04. If you multiply hydrogen, it will be 5.372. For oxygen, it's going to be 2. So still we do not have the numbers. Those are close to the whole number. So we have to multiply it by another number to see if we can get a better moles. So this time I am multiplying all these coefficients by 3. So by doing that, I have C3. This time we have 8.05 and oxygen is 3. So this time the numbers are very close to the whole number. So you can simply drop this and your answer will be C3H8O3, and this will be the empirical formula for this compound. Now this step that we did here, finding a multiplier, we did this example so that I can show you that sometime we have to do this as well, but not all the time. Most of the time you will, when you will divide these moles by the smallest number of mole, you will already get the number that is very close to the whole number, and you can just do the simple rounding and you don't really have to find a multiplier. The next problem is determining the molecular formula. So the steps to determine the molecular formula is, first of all, you need to determine the molar mass of the empirical formula. We know how to find the molar mass. We find it from the periodic table. If the empirical formula is given, you will be just adding the masses of all those elements from the periodic table, and you will get the molar mass of the empirical formula. Divide the molar mass of the compound by the molar mass of empirical formula. So here we have two molar masses, right? One is the molar mass of the compound. So this will be given in the problem. This will be given in the problem. This you will find. Then you will be dividing the molar mass of the compound by the molar mass of empirical formula, and it will give you a number that will be very close to the whole number. You are not going to do the multiplier thing that you did in the last empirical formula problem. So it will already be very close to the whole number. You will just round it to the whole number and multiply all the subscripts in the empirical formula by the number you calculated in the step number 2. So let's do the practice here. So here we have a compound whose empirical formula is this. Has a molar mass of 62.0 grams. So this is the molar mass of compound. Okay. Empirical formula is given. You have to find the molar mass of empirical formula. Let's do it here. So carbon is 12.01 gram. From periodic table, hydrogen is 1.01 grams times 3 will be 3.03 gram. Oxygen is 16.00 gram. You will be adding all these numbers, and your molar mass for empirical formula is 31.04 gram. You will be dividing molar mass of the compound by molar mass of the empirical formula. So that's what I'm going to do here. 62.0 grams per mole is the molar mass of the compound, and molar mass of empirical formula is this much grams per mole. You have 1.997, and when you round it is going to be 2, right? So the last step is you will be multiplying the subscripts in the empirical formula by this number. So you will multiply all these by 2, so you will get C2H6O2. So this is going to be the molecular formula, and if you want to check your answer, you can find the molar mass of this. You will see you will get 62.0. The last topic of this chapter is going back and forth between formula and percent composition, which means if the formula, which is the compound formula, if that is given, you can find the percent composition of each element in that compound. And if the percent composition given, you can find the formula of that compound. So we will see how to do that. So the first step actually from formula to percent composition. So to find the percent composition from formula, this is the formula that we use. Percent of an element in a compound equals grams of element in 1 mole of the compound divided by molar mass of the compound multiplied by 100. We can quickly take a look of this with the example of water. In water, hydrogen is 1.01 times 2. So mass of hydrogen element in 1 mole of water is 2.02 gram. Mass of oxygen in 1 mole of water is 16.00 gram, and the molar mass of water is 18.02 gram. So these are our numbers, right? Now if you have to find percent of hydrogen, it is going to be mass of hydrogen in 1 mole, which is 2.02 gram, divided by molar mass of the compound, which is 18.02 gram, multiplied by 100%, will give you the percent of hydrogen. And you will have 11.2097%. When you round to 3 sig fig, it is 11.2% hydrogen. For oxygen, grams of element in 1 mole of compound is 16. So 16.00 gram. Molar mass of the compound is 18.02 gram. Multiply 100%. You will get 88.79%. percent oxygen. Now, if you want to check your percent composition, if it is accurate or not, you can add all these percentages. Your answer should come very close to 100%. So what we learned here is that if a formula is given, which we started with the water formula, so if the formula is given, we can find the percent composition of each element in that compound, and you just saw how we did it, right? Now going back from percent composition to formula is what we can see in the next slide. So in this slide, we will see how to find empirical formula from percent composition. So the problem is that to calculate the empirical formula of the compound that has following percent compositions, we have 24.39% carbon. Let me actually write it down. So we have carbon as 24.39%, hydrogen is 4.08%, and chlorine is 71.53%. So percentages are given. What we're going to do is we just assume that we have 100 grams of compound. If the compound is 100 gram, 24.39% out of 100 means that we actually have 24.39 grams of carbon in that compound, right? Similarly, 100 grams of compound and 4.08% hydrogen means that we actually have 4.08 grams of hydrogen. And same is for chlorine. So once we assume that we have 100 grams of compound, all these percent signs will change into the gram. Once we have gram, for the empirical formula, we have carbon, hydrogen, and in this case, we have chlorine. We actually need to find these X, Y, and Z, right? To find moles of carbon, you have grams here, so you just simply have to convert these grams to the moles of carbon. So 1 mole of carbon is 12.01 grams of carbon. For hydrogen, you're going to do that 1 mole of hydrogen is 1.01 grams of hydrogen. For chlorine, you will do 1 mole of chlorine is 35.45 grams of chlorine. And when you divide by these numbers, you will get moles of carbon, hydrogen, and chlorine. Okay, so here we have moles of carbon, hydrogen, and chlorine. And next step is same as we did for the empirical formula. We are going to write down elements like this and their number of moles. And then we will divide these number of moles by smallest number of moles, which in this case is chlorine. So okay, so these are the numbers that we have after dividing, and you can see all these numbers are very close to whole number. So our empirical formula will actually be CH2Cl. Okay, I hope this video is helpful for you guys to learn the reaction stoichiometry and empirical formula problems.